we continue on with our presentations, and Danila Parnishchev from Kaspersky Lab will be talking about security of Verix. Or, the subtitle of his presentation is How to Launch Tetris on Your Old POS Terminal.
See you here at Standoff. Hope you are already having a good time. My talk is about Verix operating system, which is a proprietary Verifone operating system used in their point-of-sale terminals. We will get to it soon, but first let me introduce myself in brief. I'm a former application security specialist at Kaspersky Security Services, and now I'm independent researcher. I focus on reverse engineering of files, protocols, file formats, and everything else available, and security assessment of industrial control systems, automotive, network equipment, and other devices. I performed the research together with security services team, which when I was part of it. Therefore, I'm presenting this talk on behalf of Kaspersky Security Services. I'd like to begin from main entities in payments. At point-of-sale terminal market, there are three main vendors: Ingenico, Pax, and Verifone. They develop terminals and provide instruments for building applications. Acquirers, usually banks, and processing centers develop terminal applications, provide processing backend and terminal maintenance. Merchants integrate point-of-sale terminals to their systems to accept credit card payments. Consumers use cards to commit payments, and one last but not least entity is Security Standard Committee, or PCI. It develops and maintains security standards for payment sector. How can a researcher obtain POS terminals for experiments? Well, it turns out that it's not a hard task, as they can be bought in the aftermarket. Most of the time, those used terminals have all applications installed by previous owners. We managed to buy several VX670 models, VX510, VX520, and a couple of VX820 models. This talk is focused on VX670, an old terminal deprecated by PCI in 2014. Why such an old target? Well, it turned out that VX670 is a perfect device for those who start studying Verix operating system, as this device has well-known CPU. The documentation for the CPU is available online. It also has an unlocked debugging JTAG adapter and some other advantages. We will get to these details later. By this research, we would like to once again raise awareness about the internal structure and security of point-of-sale terminals. Point-of-sale terminals remain one of the hardest research subjects, as they almost always incorporate proprietary hardware internals, protection measures from acquiring firmware, lack of public development tools, and etc. During the research, we have developed tools that may help security auditors and professionals to perform audit of point-of-sale terminals, and we would like to introduce them to public. And of course, we are here to have some fun. As we will see, point-of-sale terminals are very interesting for research, very interesting research targets, and hard tasks for hardware analysis. You can find many research of point-of-sale terminal security in the network. I would like to mention the two recent works. One is the successful attempt to exploit a vulnerability in Linux-based Verifone terminal and use it as a gaming console, performed by Nolan Ray at DEF CON 25. And the second resource is DEFCON Safe Mode Payment Village. It gathers several talks by such experts as Alexei Stennikov, Timur Yunusov, Arkady Litvinenko, Steven Murdoch, and others. It is a well-done source of information about payment systems and aspects related to them, including point-of-sale terminals. I highly recommend checking this resource if you are into payment system security. Well, the VX670 is not as powerful by hardware, so we won't be able to run Doom on it. However, we will see how to run some Tetris games on this device. And now, let's move on to the agenda of the talk. I will describe our research of VX670 terminal, from gathering information about the device into getting firmware analysis and finding vulnerabilities in it. Also, I would like to show some instrumentation we have developed during our journey. So, let me start from information gathering part. VX670 terminal has a mini HDMI port, a magnet stripe reader, EMV card reader, SIM and SAM module slots, and keyboard, and of course display. By the way, that mini HDMI port is used not for connecting external monitors to the terminal. It has a custom pinout. If you are a happy owner of a debug interface shown on the slide, you can easily restore the pinout. HDMI multiplexes USB host and client, COM port, and power socket. Thus, we append USB and COM ports to external interfaces. Actually, these debugging interfaces are not very easy to buy. They are quite rare. We even had to fix our own cable when its mini HDMI adapter got broken. After external interface enumeration, we proceed with documentation and SDK. Documentation can be found in the internet, as well as the SDK. And I would like also to mention that the SDK contains a C compiler for the POS terminal and Verix operating system. It is called Verix CC, and it is based, it internally invokes ARM CC compiler. And the DDL utility is the tool used for loading files into POS terminals. However, all binary executable files and shared libraries should be signed in order to be executed on the terminal. Here is the help for DDL utility, used for download files to the terminal. It's used for both loading user files to the terminal and for updating firmware of the terminal. From the terminal side, we can access system mode by pressing F2 plus F4. Usually system mode is password protected, however, commonly the password is default. System mode allows several actions. The most important one is putting the terminal into download mode, from which it is capable of receiving files. File loading is performed via COM port of the device. However, if debug configuration parameter is set to 1, it will be used to output debug logs from the terminal. Configuration parameters are special parameters of Verix operating system. They look like environment variables in Linux, and they are stored in a special file called config.sys. The following slide shows an example of debug output from the terminal while operating system boots. Green color highlights file system initialization, while blue color highlights loading of program modules, and the purple color highlights running of main system application. We have an ability to load files and some debugging output. Now let's see how we can get the firmware of the terminal. Firmware updates for point-of-sale terminals and update instructions can be uploaded from the internet officially, usually from distributors of point-of-sale terminals, like for example InPOS company. There's also additional information about POS terminals firmware updates available in the network. On the slide you can see one of the web pages that clearly explains us that we shouldn't try to extract firmware files as they are securely protected with a password. Back to the firmware package loaded from InPOS web page. Updates can be performed using a graphical tool called POS Loader, which internally invokes DDL for loading applications and file system and operating system to the terminal. Point-of-sale loader uses password-protected zip archive with actual firmware. Password for the archive is of course hard-coded into the POS loader, so after a bit of analysis, we can easily extract the password. A password-protected archive contains a bunch of encrypted files and the signature of the package, vfi.p7s. As there are no clues about encryption method used, it may seem as a dead end. In this case, it is always useful to try to get firmware for the device using hardware debugging interfaces or dumping memory chips. The following slide shows main chips of the board of the terminal. There are a CPU, flash, and RAM chips. The CPU is well known and the documentation is available in the internet. So we can leverage two methods of obtaining software: JTAG and connecting to CPU's JTAG and dumping its memory, and dumping flash memory directly from the chip. We chose the JTAG approach. We managed to find JTAG pins on the board. However, the TCK pin, which is a clocking pin for JTAG debugging interface, was not connected to them. We had to connect it directly from the CPU and soldering the chip. One more problem to solve is that the terminal has many anti-tampering mechanisms that detect whether the case is opened or not. When we start the device in disassembled mode, it won't boot as usual. It will show us tampering log and refuse to boot the operating system. Therefore, we had to add a lot of additional wires to connect all anti-tampering circuits and make the terminal boot the Verix operating system in disassembled mode. The red board on the screen is the JTAG adapter USB bus blaster. This setup worked for us and we were able to dump the firmware with OpenOCD. We found Verix operating system kernel at address 0x all zeros. And using information from debug output from the COM port, we also were able to dump firmware modules. At that point, we got all required data to start our analysis, so we are moving to the third part of the talk. This slide demonstrates Verix operating system structure. The kernel is not monolithic, it consists of separate modules, each of which handles a specific task. For example, loading user mode applications, task scheduling, system upgrades, and etc. Below this kernel lie drivers that control file system and external hardware interfaces. Both kernel and drivers run in supervisor mode, while applications run in user mode. There are two types of applications: user applications and system applications. System applications come with the operating system, and among other system applications is the one important application called system mode application. All applications communicate with the kernel via supervisor calls. System mode application is an analog of init process in Linux. It gets started by the kernel after operating system initialization, and then it runs user applications. The user application to be loaded is defined in an environment and configuration parameter called *go variable. It is also located in config.sys file. Here's the boot log once again. You can see different modules of the operating system loaded into different addresses, and among all these modules, the one that draws our attention is called upgrade.tmp. It is responsible for firmware updates, and by studying this module, we were able to recover the encryption method used for firmware update files. Here's the algorithm used for firmware decryption. First, let's look at the top of the slide. The file vfi.sys is just a renamed vfi.pid file. It gets renamed by upgrade.tmp module before decryption. It is decrypted by DES in ECB mode with key hard-coded to the module. Next, it goes decrypted by unknown algorithm. We were unable to reconstruct the algorithm, so we used Unicorn engine to emulate upgrade.tmp code responsible for decryption of the file. Decrypted VFI.sys file contains several keys used in order to decrypt kernel and file system images. Both the kernel and images are also encrypted by DES in ECB mode with different keys. Now let's look at the structure of a file system volume. Each file system volume contains several file system entries following each other. One example file system entry is displayed on the slide. As you can see, each file system entry has file size, file name, and file body. File entries follow each other within one file system image. There are a lot of file system images in Verix operating system. They are all marked with different letters. The most interesting ones are I and F. These file systems are used to store user files. And also other file systems mostly store system files and utilities. File system directory tree in Verix operating system is not supported. However, file system mechanism incorporates security groups. They are used to restrict access to files for different applications. The operating system implements 16 file groups. Group 0 is reserved by system, and all system files belong to group 0. Group 1 is the most privileged group. Applications from group 1 can read files from all other groups except for group 0. And group 15 is a public group. Applications for all other groups can access this group. In addition to security groups, executable files have authenticated flag. It is set when the application's signature is verified successfully. Access to security groups from system mode menu is protected by different passwords. User mode applications work in virtual address space. They may share libraries. There is one standard library called sys.lib, analog of standard libc in, for example, Linux. User mode applications interact with kernel space code by invoking supervisor calls. And supervisor calls are partially documented. Some of them are not listed in developers' manuals and SDK headers. So we have to analyze kernel and modules in order to find out their meaning. In addition to that, Verix applications have a proprietary executable format. By analyzing application loader, we were able to gather all the information about the format. Let's observe it in brief. But before that, I would like also to mention that there is one useful tool in the SDK called Verix HDR.exe, which is an analog of readelf tool in, for example, Linux. It shows basic information about executable files and shared libraries. Now let's proceed with the format of the executable file. The first byte is a magic byte that shows whether it's an application or a shared library. The next byte incorporates several bit flags. Next 2 bytes is a file version. Then goes code section size, code loading address, data section size, and data start address is not presented in the executable file because it is calculated as code loading address and plus code section size. Next goes stack size of the application, heap size, and the program entry point. After that fields goes a field with dependencies. It enumerates all shared libraries that needs to be loaded in order prior to loading the application. This slide demonstrates Verix virtual memory map. Kernel space lies at address 0x all zeros, and user space lies at addresses starting from 0x 7 all zeros. And at the very beginning of the user virtual memory segment goes a system section reserved by sys.lib standard library. Each application has a stack segment, code segment, data segment, heap, and also a virtual memory address pool containing all shared libraries. Now I would like to discuss Verix system applications. And let's start from the main application called sysmod.out. This application is an analog of init process in Linux, the first process started by kernel after its initialization. Its main purpose is running user application, the one defined in Go configuration parameter in sys.cfg. Additionally, sysmod.out hooks key combinations 7 plus enter and F2 plus F4. It verifies the password for entering system mode and draws system mode menu when the keys are pressed. If the start button is pressed in system mode menu, the terminal switches to uploading mode. From that mode, it is possible to download all user files and applications from the terminal through COM-port. We cannot download system files from access group 0, and that means all system binaries are not accessible that way. Only user applications and files. The protocol used for uploading is the same as for downloading. This protocol is almost text protocol, and its format can be easily analyzed. There are some other system applications worth mentioning. For example, that binary with hard pronouncing name padgrdfa.out, it verifies signatures of executable files and shared libraries. Then goes one smrkl.out system application that is used for loading keys into the terminal when it's put in key loading mode from main system menu. And the unzip.out utility is used just for uncompressing zip archives. Now let's discuss the new instrumentation we were able to develop during our research. First of all, we developed an IDA loader for Verix applications. It parses custom executable file format, analyzes file headers, loads the binary to IDA, marks code, finds entry point, and creates additional segments like data segment, stack and heap, and also it marks all calls to standard sys.lib library and creates the sys.lib section for binary. The next useful plugin is a IDA script that helps reverse engineering kernel and modules by parsing supervisor calls. It enriches IDA output with additional information, for example, supervisor call names and all arguments used by a particular supervisor call. This plugin is actually implemented more as a dictionary and enumeration of all supervisor calls with their description of their parameters and returning value. And after analyzing the application code, this script just finds supervisor calls by their numbers and changes IDA's microcode a bit in order to transform supervisor call instruction and that assembly entries to the code into just invoking functions, which is much easier to understand and analyze. There is also a script that unpacks Verix firmware images for all terminals. It is capable of decrypting firmware updates gathered from the internet, for example, from firmware updates from InPOS site. However, it works only for old modules like VX670, because for modern models like VX820, the encryption method was changed, and as well as the keys for encryption. It is also a Python script. And one more utility we were able to develop is a Verix.com uploader. If we put the terminal into uploading mode by pressing star button while in system mode menu, the terminal goes to upload mode, and we will be able to run our script. But first connect, of course, the terminal to the PC via COM port, then run our script, and it will dump all user files from the terminal. Next, proceed with vulnerabilities and discovered during our research. As I already mentioned, Verix operating system verifies signatures of all applications and shared libraries prior to loading them into memory and executing them. Each executable file should go with a signature file with extension .p7s. This file contains the certificate and a signature of a binary. .p7s files are encoded with ISN.1 ter notation, and in order to check a signature, Verix operating system runs special system utility called padgrdfa.out. And only system applications like that padgrdfa.out application are granted permission to mark files as executable by calling a specific SVC. We call this SVC file supervisor call set authenticated, because this supervisor call is not documented and has no name for developers. The example signature file encoded in ISN.1 is shown on the slide. The green mark highlights the signed file name field of this signature file. As you can see, it's EA5 string, and the example file shown on the slide is called env.lib. So that means the signature file is designed for env.lib, shared library. Now let us look at the vulnerable code that parses this signature file in padgrdfa.out. First of all, the function from pad.lib called pad-get signed file name is called in order to parse the signature file and get the signed file name, to find this EA5 string and parse the name. The name is placed into local variable called signed file name. This code line is highlighted in green. After that goes a check of signature. For that purpose, the function pad check signature is called. It also resides in pad.lib library, and it verifies signature of the file. That means it calculates the hash of the file extracts the hash signed by private key in the certificate .p7s and verifies those hashes against each other. And if the check is failed, a bunch of actions is performed, and the final action only shown on the slide is SVC restart. This means the call to a special supervisor call that restarts the operating system. In the opposite case, the supervisor call file set authenticated is invoked in order to mark the file as authenticated and thus ready to be executed. This code is executed every time the binary is loaded to the point-of-sale terminal. Now let us observe the stack frame of the function. The signed file name variable occupies 36 bytes. And if the name of the file is longer than 36 bytes, then the overflow occurs, corrupting stack frame and overwriting, and using this vulnerability, a potential attacker may be able to overwrite link register address saved on the stack. Link register is a standard ARM register, and thus gain control over execution flow. So it seems like an exploitable bug. However, let's once again look at the code. In order to gain control over execution flow, we need the instruction return to be executed. So we need a standard exit from the function. However, here we can see that supervisor call restart is called at the end, and that means no exit from the function will be performed, as well as the operating system gains control after call to restart function. It immediately shuts down the system, and the return code for the vulnerable function will never be executed. So now it seems like a big nothing. However, let's once again analyze memory of the running process in Verix operating system, specifically PAD-GRDFI.out. Here it's simple memory layout. At offset 0x7 and all zeros goes standard system library, then goes stack of the application, which is readable and writable, and after the stack go code segment and data segment. So the code segment is the one segment where the vulnerable code resides. And here's the layout of the stack. It turned out that at the very bottom of the stack lie base addresses of all shared libraries used by the application, including pad.lib. And pad.lib contains such call as pad check signature. And if you remember, this function is called in order to verify signature of the file. Its offset is 0x20 from pad.lib base. So if we overwrite, so if we make our file name too long and it overwrites shared lib's base addresses, specifically pad.lib base address, then the offset to the function will be calculated incorrectly. And instead of pad check signature function, the code of our choice will be executed. So this again seems like a promising vulnerability. And here is the 100% valid signature file. I will highlight the field in ISN.1 notation that encodes file name. It's an ASA.1 EA5 string with length 0x200. And it contains our signed file name, and at the very bottom of this ASN.1 structure goes our forged address pointing to pad.lib base address. However, it now points to the code highlighted with red mark at the top of the slide. As you can see, this code simply puts signed file name into register R1 and then invokes supervisor call file set authenticated, which means that our file will be marked as executable and will be executed after next reboot of the system when we upload user application to the terminal. So let me show you the demonstration how this can be leveraged in for playing a simple snake game on the terminal. Here's the video. First of all, we connect mini HDMI cable to the terminal and download our application with forged signature. Then the operating system verifies the signature and thinks it is authentic because our exploit worked. Proof of concept exploit worked. And now we are able to play a snake game on the terminal. That is not a very interesting game. And as you can see, at the bottom of the frame, there is our debugging cable connected to the terminal via mini HDMI port, and it is used for uploading files to the terminal. Vulnerable models of the terminals are VX670 and VX510. That is basically all I would like to tell you, and now let's summarize the research. We developed several instruments, including utility for downloading files from terminals, IDA scripts to simplify point-of-sale binary application analysis, and found several security issues, including unlocked hardware debugging interface JTAG, hard-coded firmware encryption key, and several signature flows, including the one I demonstrated you today. The other two signature flows were minor and did not have a specific impact, so I'm not discussing it in the presentation. However, they will be described in our white paper. Here's the vendor response. Of course, during our research, we followed responsible disclosure procedure, and we notified the vendor about all findings. The response was that these terminals reached their end of life in 2014, if I remember correctly, so they don't receive any updates. Here's our disclosure timeline. Our research finished somewhere in September 2019, and right after the research, we informed the vendor about all found issues. And approximately within 1 week, we received a response. I was showing you on the previous slide. And now is our public release. I would like to say thank you to Kaspersky Security Services team, and especially to Radu Motspan, Alexander Tlyapov, Kirill Nesterov, Alexei Osipov, Alexander Zaitsev, and Gleb Gritsay for helping me with this research. And I would like also to say thanks to Verifone Security team for their quick and prompt responses to our letters. White paper slides and tools are to be published at official Cal Security Services GitHub, so stay tuned. I'm sure there is more interesting to come. And now I'm ready to answer your questions. Thank you for your attention.
Thanks, Danila. Do you want to keep conversation in English?
Yes, why not?
Okay, so everyone, we would like you to embrace you need to ask questions in our chat, because based on my experience, based on probably every speaker's experience, if there is no questions after the presentation, that sometimes can be quite devastating, detrimental. So please ask questions. So I have a few questions. First of all is, why Tetris? Don't you think that as a security community, we need to move forward and be a little bit more creative and stop playing Doom or Tetris, because there are so many other games, to be honest?
Well, well, that was, I think, the thing that came to my mind first. So I decided to implement a Tetris game as a demonstration. Yeah, maybe you're right, and we need to go further and to more modern models that have more productive hardware, more efficient hardware, and we can play much more interesting games there.
All right, what do you think is the major sort of issue in all kind of payment terminals, point of sales, PIN pads, like top one?
Top one issue?
Yeah, like in general, like lack of, I don't know, security measures in place, security through obscurity, outdated software. Because, you know, if you, for example, say, what is the main problem in ATMs? And people will say, hey, Windows XP, as an example, which is actually not correct, but you know what I mean.
Well, I think the common problems with the terminals are the same as for any other sphere. It's passwords, weak passwords that do not change, and maybe yeah, that all that comes to my mind, I think. And I think that proprietary operating system may be also not as a good choice for a terminal, as can be also seen that Verifone migrates to Linux operating system now. Maybe it will be better and more easy to keep Linux-based terminals secure instead of maintaining that proprietary operating system. Well, I don't have, I think, a lot of statistics about usage of other point-of-sale terminals except for Verifone, I think. So it's hard to say for the whole industry for me.
Well, that's still a good point. And the next question associated with your last point is, what are your plans for next research? Any ideas to dig into other point of sales? Anything?
It is still a point to think about.
All right. Are you planning to release tools you mentioned?
Yes, we are. It will be available, I think, at our official GitHub. You can find the link on the slides.
Well, thank you so much. Thanks for the presentation.
Thank you for your attention.